Welcome back. So we are in the middle of the discussion of this momentum theory. So what we have kind of done so far, we looked at that one-dimensional momentum theory. So that essentially, looking at this one-dimensional, there we have CP max, CT max, all these limits. And essentially, this is where the power coefficients, the Bethe limit, which was derived from here, this kind of came from the maximum or optimum power coefficient and things like that. Then we have looked at the momentum theory with weak rotation. So the first one, when we kind of talked about initially, so it doesn't consider the rotation of the wake, but the rotation of wake can have significant impact in the flow field or the parametric calculations, and then from there we looked at the Behm theory, which is so these are the things that we have derived so far, and I think we have stopped with this kind of conditions in the last session. So from here we'll move on, and we'll now look at the Behm example. So probably that would make things much more clear, where we'll look at some Behm example. Okay, let us assume a few typical values. Okay, let's say lambda r, which belongs 1 to 7, number of blades 3, lambda r is 7 and a equals to 1 by 3 for all r. Here the consideration is that we are trying to extract or extracting maximum power due to Bethe limit. Okay, so this is what we are trying to kind of do. So if I draw the system, so let's say so this is some strip here where lambda of r is r omega by u infinity, that is r, and this distance is small r. This is lambda of r omega, which is 7. Okay, so here what we have is CL equals to 1, CD equals to 0.01. So the idea here is that the twist and pitch optimally chosen so that the angle of attack alpha is constant at 5 degrees. So that is something so now here A prime is something A1 minus A by lambda r square, 2 by 9 into 1 by lambda r square. So what you kind of get to see is that 1, 2, 3, let's say 7. So this goes like that, and it kind of come to a, so this is 21%. Somewhere you get 5%, and this one is something 2.5%, and this is 0.5%. Okay. So this direction, lambda r with increasing r. So that's what you have. Okay. Now, what we can get, we estimate the local solidity using equation 35b. Okay. So what we get, sigma r 4a 1 minus a CL lambda r 1 plus a prime CD 1 minus a dot root over of lambda square 1 plus a prime square plus 1 minus a square. So what we get 8 by 9 1 by lambda r 1 plus a prime plus 0.006, which is equivalent to 0, 1 by lambda r 1 plus a prime 1 plus 4 by 9 1 by a prime lambda r. So this is also kind of equivalent to 0. So what we get is that 8 by 9 1 plus a prime square, which is 8 by 9 1 by lambda r square. So that means my variation of the solidarity, this is lambda r with increasing r 1, 2, 7. So this is sigma r 89%. This is 22%. This would be 2%. So that is how the solidarity varies. Now, what so what we can find out, so essentially point here is that what does this mean for chord length of C? What does it mean? So we can, since sigma r equals to B into C by 2 pi r, we have 8 by 9, 1 by lambda r square. Now we know C equals to 2 pi r by B by 9 r square by r square 1 by lambda r square. Okay. So that gets us 2 pi r B lambda r square 8 by 9 into 1 by mu. Okay. So mu is R by R and lambda R is mu lambda. So this can have mu R lambda by U infinity R omega by U infinity. So this should become 2 pi R by B 2% of 1 by mu. So which is 4% of R by mu. So that means what happens is that let's say this is R equals to 50 meter, this is 2 meter, 10 meter. So that tells two important things here. One is that wick rotates more if the turbine moves relatively slower, that is low lambda, and higher lambda leads to low wick rotation. What you get from this, so what you get from here is that the wick rotates more when the turbine moves relatively slower, and that is happening towards the hub, which is this portion of this which is close to the hub, and always towards the tip it rotates more, so the wick rotation would be less. So the majority of the impact of the wick rotation would be visible towards the hub or of the blade. Okay, that is what is in one of the. So what it does tell us is that, so it's one of the design consideration that you will obtain from this kind of analysis, and that tells you that what you should consider and what and how you should consider. mm, mm, uh, these are the things one has to kind of consider during the design part of the. Now there are other things important equation which obviously to remember. uh, Lambda R is R by R into lambda, which is always greater than 1, CLCD greater than 1. These are assumption. Now from axial momentum balance, force on blade area, AB equals to half rho AB lambda R, which is essentially W square. So this we can think about like this kind of annulus where it cuts through. So this is A and this is AB. So equals thrust on annulus if A equals to U infinity 1 minus A U infinity 2A half rho A U infinity square 4A 1 minus A. This is CT of A. We have local solidity, which is sigma r AB by AA, that is B into C by 2 pi r. Now we can find out optimal chord. So half rho U infinity square AB into CL lambda r square up rho U infinity square 4A 1 minus A. We get sigma r CL lambda r square 1 by lambda r square, where A equals to 1 by 3, which is optimal. Okay. What we do, 2 pi r into B CLR 8 by 9 1 by lambda square r square by r square. So C by r 1 by B 2 pi by 9 8 by lambda square r square by r, which is proportional to 1 by r. What you get, one can see, so if this is r, your C by r is proportional inversely r. So this tells us one thing. Basically, for fixed CL at a optimal angle of attack, optimal chord inversely proportional to radius. So this also tells us from this momentum theory how the chord is also varying, because if you see this location, you have different chords. Here is the different chord, here is different chord here. So in horizontal axis wind turbine, which is very typical, when you move away from the rotor hub towards the tip, there are different kind of airfoil with different kind of chords which are used. So that is another or important design consideration, that one has to take into account while doing all this design. So it's like in totality, you have to see that what we can look at is that linear taper, practical blade design. Okay. So in practical or in practice, linear taper is also used. So this is what it kind of it shows. So this is what it is. So this is the linear taper part. Okay. Is also used because the cord close to the hub is shorter. To compensate for the lower solidity, one can increase the angle of attack in order to increase CL of R accordingly. Here, the drag loss in the inner part of the blade is less important to us. Now, we have already looked at the flow angle and all these things. So just to recap that part. So this would be beta, this would be alpha, this is phi, which is alpha plus beta. And this is the direction of the W. And that is chord line. So here beta is twist, alpha is angle of attack. So alpha becomes phi minus beta. So for fixed alpha, for the best CL by CD. So what you can do, you can optimize the CL by CD, which is going to be the best. For that, you can fix the alpha. So what you have then, you have sine phi, which is 1 minus a lambda r 1 plus a prime 1 plus 1 minus a square 1 plus a prime square, which is equivalent to 0. So that gives you 1 minus a by lambda r 1 plus a prime, which is 2/3 1 by lambda r. A equals to 2/3 and a prime equals to 0. So this is what you get. So now if you plot, let's say if I plot phi, so this might lambda r with increasing r 1 to let's say 7. So that goes like this. So this could be around 42%. This can 42 degree, this would be around 5 degree like that. So P would be sine inverse 2/3 R by R lambda, 2/3 R lambda into 1 by R. So which is inversely proportional to R. Okay. So another plot which we can look at it is the similar way. 1, 2, 7, which is beta. So beta can vary like in the similar fashion as well. So here it could be around 37 degree. This can go to almost at when go to 0 degree. This is where it varies. So for, let's say, given profile CL, CD and alpha fixed at alpha not equals to 5 degree, then you can see that what happens is that this is CL variation with alpha. And this is alpha. This is CD variation. This could be somewhere optimal point. So what you need to consider is that you try to optimize CL by CD. So you basically optimize or best CL by CD, you try to have it. And for that, you fix the alpha, and then the rest of the parameters can be determined. So these are all goes in kind of an design consideration and all these things, how this momentum theory can be applied to the design. Obviously, one can, I mean, these are initial design you need to have. One can have complete numerical based uh, mm, complete numerical based data and carry out this design. Okay. So now what we would like to see, because now we have seen that these aerofoils and all these things, then the thing what is important to discuss now, what kind of airfoils or how the airfoil behaves. So some discussion on airfoil that we are going to do, and also we're going to talk about wick and all this before we move to the other part of the discussion. Okay, that we continue in the second other session. Thank you.